Hey folks, welcome back to part 2 of Basic Concepts of Probability. So I have a question E for you. According to the United States Census figures, on July 14th, 2018, there were an estimated 162.4 million males and 166.9 million females. If a person were selected randomly from the population in that year, what is the probability that the person would be a male? Okay, so the probability of a male. All right, so we know what the sample space is. The sample space is all the people in the United States, right, that the census recorded. So we're trying to find the probability of being male, and M will work just fine for that. But try to use that notation. The capital P represents probability, and in parentheses is what your event is, the probability of being male. Now we know right there were 162.4 million males. Now notice I'm going to leave off, well, no I'm not. Let me be a good mathematician. 162.4 million males. Now, we need to divide by that by how many people there are total. Do we know that? I don't believe we do. They didn't tell us how many total there were. So you know what? We're going to have to find out. We're going to have to add 162.4 million plus 166.9 million. And that'll give us the total number of people in the United States that the census found out in 2018. Okay? Or what it was recorded then. There wasn't a census in 2018, I don't believe. So 162.4 plus 166.9, remember this is in millions, that's 329.3 million people. Okay? Now it didn't say at all how we should reduce this or anything. We could write this as a decimal, but it didn't say to round. So how do we write our final answer? Now one thing we can definitely do is cancel the millions, because we have million on top and million on the bottom. That's just like dividing both by a million. Boom, it's gone. Now, since we already have kind of decimals in our answer, I don't believe there's any trouble in writing this as a decimal. So I'm going to take that 162.4 and I'm going to divide that by 329.3, and I've got 0.493167325. Again, I don't see where it says to round. I'm going to write down everything. 493167325. Now, I do believe you should always look at your answer and see if it makes sense. You remember 0.5 is half, right? That's 50%. Notice this is almost half, 0.493. And we know those numbers are close together, but there are less males than females. So we have probably done this right, okay? 49% roughly are males. And we have this thing called law of large numbers, or law of averages, it can also be called. It says, as an experiment is repeated more and more times, the proportion of outcomes favorable to any particular event will tend to come closer and closer to the theoretical probability of that event. That's a whole lot of words. Basically what it says, you remember our cup experiment? When we tossed the solo cup in part 1 of the video, we did it 50 times. What if we did it 500 times instead? Well, the numbers that we get are going to come closer and closer to the theoretical, which is the actual mathematical probability of that cup landing on either normal or on its top or on its sides. If we did it 500,000 times, it would be even closer. So that's what it's saying. If you do an experiment, the more number of times you do that experiment, the closer your numbers are going to be to the actual theoretical mathematical probability of that event occurring. Now, I got a problem to go with this. It says a fair coin was tossed 35 times. Y'all, that's a bunch of times to toss a coin. And you can certainly do it. It really wouldn't take all that long. I say it's a bunch, but it wouldn't take all that long to toss a coin 35 times. It'd take longer to record it. And that's what they did here. Now notice these are not different events. they just divided it up into 5. So you got tails, then heads, then heads, then heads. And then on the 6th toss, you got tails, and then tails on the 7th, tails on the 8th, and then heads on the 9th, heads on the 10th. You see what I mean? That's all 35 tosses listed. It says, now calculate the ratio of heads to total tosses after the first toss, and then after the second toss, and then so on through all 35 tosses, and plot these ratios on the graph. Okay, so what are they saying? So we're going to do this by hand, and then I'm going to show you the typed up version of this answer. So it says calculate the ratio of heads to total tosses. So I got 0 heads to 1 toss from my first toss. The second toss, I got 0 heads out of 2 tosses. The third toss, look, finally got a head. I got 1 head out of 3 tosses. On the 4th toss, now I have 2 heads out of 4 tosses. Hey, there's a 50% right there. On the 5th toss, I got 3 heads out of 5 tosses. You see what I mean? And on the 6th toss, I didn't get a tail, so I got 3 heads out of 6 tosses. There's my 50% again. And then on the next toss, I still don't have a head, so it's 3 out of 7, and the next toss is another tails. So I got 3 out of 8. You see what I'm doing? I'm just counting the number of heads up until that point. If I keep doing that and plot it on the graph, let me show you what happens. So notice they changed it to decimals, okay, and they didn't even go as far as we did on the list, but they plotted those values on an XY axis, and it's the outcome I'm really trying to show you. I'm not stressing over whether you can plot on the XY axis. I want to show you what happens. Look how far above 50% and far below, or half. Remember, right there is half. It's 0.50. And so it falls below, way below 50% in our first two. Remember, we got 0 and then 0. But then the next point, we got 0.33. So that's here. And then it jumped up to 0.5, which is the theoretical probability, right? And then it jumped up to 0.6 and then back to 0.5. But look, the further you go this way, see how the closer and closer it stays to the average? And that expresses that law of large numbers. The more tosses you have, on average, you're going to get half of those guys as tails and half of those guys as heads. And that was just 35 tosses. What if we did 3,500 tosses? Then you would see it stays right there at 50%. Okay, kind of neat, right? A little bit more goes with that. Comparing empirical and theoretical probabilities. It says a series of repeated experiments provides an empirical probability. Remember, experiment and empirical go together. Like the cup problem, which by inductive reasoning is an estimate of the event's theoretical probability. Because if you don't have theoretical, you just have to come up with an estimate, and that's what the experiment is all about. It says increasing the number of repetitions increases the reliability of the estimate. We've already talked about that a few times. This is just putting it in green and making it official, right? And this is likewise an established theoretical probability for an event enabled us by deductive reasoning to predict the proportion of times the event will occur in a series of repeated experiments. Notice the difference too. It says inductive reasoning, so you're supposed to imply from your theoretical from your empirical probability the theoretical probability. On the other hand, if you have the theoretical probability, you can deduce what's going to happen in your experiment backwards. And that's almost obvious probably for a lot of people, but it needs to be stated. Now, let's go back to our problems. We can apply probability to lots of scientific study, but genetics is one of those examples where we can apply probability. And Gregor Mendel, who studied genetics very early on, studied fruit flies, I do believe, and studied pea pods. The experiment I'm going to show you is dealing with pea pods in flower color. So here we go. An example, a flower color in certain pea plants follows the rule. And I say pea pods, really pea plants. It's the flowers we're looking at, not the pods. So pure red crossed with white produces pure red. So if you have a plant that has a red flower and you pollinate that with a plant that has a white flower and they produce offspring, it's going to be red. which means what we call this is red dominant. So whenever you have a dominant, usually we use that letter capitalized, and white is recessive in this particular situation. So instead of using a W, we're going to use a little r because it's recessive to the red. Then you can create these squares. Look at this. So you have the first parent on the side, and the first parent is going to give 2 genes, and the second parent is going to also give 2 genes. Remember, the capital R represented red, and then the lowercase r represented white. Now, when you put them together, the capital R red paired up with the R from the second parent, you get a capital R little r, and then here you get a capital R little r again, and then here you get a capital R little r again, and then you get a capital R little r. Notice that every one of these offspring would be red, right? That would have to be, because if red is dominant, then the red's going to win out. Kind of like blue eyes is dominant, so the blue eyes win out. Now, here's the fun part. What if these offspring have more offspring? So watch. So the second to third generation. So the first parent, remember, is a big R, little r. So they have they're a red plant, right? But they have genes to pass on that's red and a white, and the same thing with the second parent. So the 2 reds go together, and then the red and the white go together, and then the white and the red go together. But finally, look at this. Look at this. We've got a white that comes out of this. So little r, remember, is white. So from this, I have a question, and then you'll see some of these in the homework as well. So it says, referring to Table 3. By the way, Table 3 is our second to third generation. We'll go back to it in just a minute. So referring to Table 3, determine the probability that a third generation offspring will exhibit each flower color. Okay? Base the probabilities on the sample space of equally likely outcomes. And notice they have the sample space for you right there. Okay? So RR. Funny, right? R. Anyway, capital R, remember, that's red. Capital R, little r is also red. Little r, capital R is red. This dude down here is the only one that's white, because you go with the more dominant. You go with the capital letter. But if neither one of them are capitalized, then it's going to be whatever the lowercase letter is, which is white. So, to calculate the probability of being red, notice 3 out of 4 of them are red. So there's your probability right there. 3 out of the 4 are red. What about white? Well, only 1 out of the 4 ended up being white. So that recessive comes out. And it's neat when the recessive comes out, right? It's pretty awesome. Now I want to talk about odds. And you hear about odds if you do any gambling. Of course, you hear about odds. That's very important. Say you're going to bet on a basketball game, and I hope none of you do, because you can really lose it. But it's like throwing away money. But anyway, if you decide to do that, you really want to know the odds of your team winning or losing, and that would tell you if it's a good bet or not, and it also tells you how risky you're willing to be. But anyway, the definition of odds. If all outcomes in a sample space are equally likely, and if A of them are favorable to the event, and the remaining B outcomes are unfavorable to the event, then the odds in favor are A to B, and the odds against are B to A. Okay, so let's think about that for a minute. Okay, so again, we have UCLA playing Michigan, right? Let's say it is 5-3 favorable that UCLA will win. So that is the odds that UCLA to win, 5-3. That means they'll win. If that number is bigger than that number, that means that the odds are in favor of UCLA winning. And you could also flip it around. The odds against UCLA winning would be 3-5. You could flip it around. So that's what this is saying. All right, so let's look at a problem. It says, what are the odds in favor of rolling a fair die and it landing on an even number of dots. You know what a die looks like, right? It's just one fair die. What are the options? You remember? So you could have a single dot, you could have 2 dots, you could have 3 dots, you could have 4 dots, you could have 5 dots, and the last possible outcome is you could have 6 dots. Those are awesome die, don't you think? Okay, so what are the odds in favor of rolling a fair die and it landing on an even number of dots? Well, let's figure out our even number of dots. Hey, that's an even number of dots. That's an even number of dots. And that's an even number of dots. Okay, so what are the odds in favor of rolling a fair die and it landing on an even number of dots? So 3 to what? Well, what's not favorable? 3, right? 3 of them are even and 3 of them are not even. So 3 to 3. Now listen, that can be reduced. If you take your odds and you can divide it by the same number, you can reduce it. So 1 to 1. You know what that means? It's equally likely that you'll roll an even number of dots or roll an odd number of dots. It's exactly the same. So there is not an advantage of even or odd when you're rolling a fair die. Okay, let's keep going. Now I got another question. Bob has purchased 15 tickets for an office raffle in which the winner will receive a beach vacation. Awesome. If 75 tickets are sold altogether and each has an equal chance of winning the beach vacation, what are the odds against Bob's winning the beach vacation? All right. So Bob's hoping to go to the beach, right? And he purchased 15 tickets and only 75 are sold. This is looking pretty good, right? So in favor, let's see, let me read the question. What are the odds against Bob winning? Okay. So if they choose one of the 15, that would be for Bob winning. But how many did he not purchase? Well, how about we do 75 minus 15? How about I get my calculator to work? 75 minus 15, like I needed to do that in my calculator. How about 60 against Bob winning? So if they draw out one of the 15 he drew, he would win, right? If they drew out one of the 60 he did not purchase, then he would not win the vacation. So the odds against Bob winning would be 60 to 15, right? But we got to reduce that. You know what? They both divide by, first you might notice they both divide by 5, but actually they both divide by 15. And you know that 60 divided by 15 is 4. So I have 4, and 15 divided by 15 is 1. So he has a 4 to 1 chance of not winning, but it does mean he has a 1 to 4 chance of winning. So it's a pretty good chance he would win. It's not assured, but a pretty good chance he might win. Now, got something new for you. Converting between probability and odds. You can go back and forth. They are not the same. And if you Google the odds of something, I have noticed that they like to give you the probability rather than the odds, which is interesting. They're not the same, but you can convert from one to the other. So let E be an event. It says the probability of E is A over B. We know this, right? So if the probability of E is A over B, that's the fractions we're used to, where A is the number of times that favorable event happened over B, the number in the sample space. Okay? Then you could change that to odds by saying the odds in favor of E are A to B minus A. Now actually, I don't think about it in formula form like this has got it written. I just think about for and against, kind of like we did the last problem. And then you could do it the other way. They could give you the odds, so the probability of the event E, okay, is A over A plus B if it's in odds form. So let's see if we can do this particular problem using that information. Okay, there's a 60% chance of rain tomorrow. What are the odds in favor of rain? So you notice now it's in probability form. So the probability of rain, or event E, is 60%. Now, we don't need it in percent form. We need the probability of rain in a fraction, right? Now, 60% really means 60 out of 100. which can be reduced to 6/10, right? Just cancel those zeros, which could really be reduced to 3/5. 60% and 3/5 are the same guy. Okay, now we change this to odds. So the probability that it's going to rain is 3. Okay, so the odds for rain are 3, 2. What are the odds against rain? It's not 5, because 5 is the total, right? If 3 of the things is going to rain, then how about 2 of the things it's not going to rain? Did that make any kind of sense to you? So if 3 out of these 5 is going to rain, then 2 out of those 5, it's not going to rain. So the odds for rain are 3 to 2. How about the odds against rain? Well, it's that same 2 to 3. Because more than likely, with 60% chance of rain, it's going to rain, right? So that's why the odds for rain is 3, bigger number than 2, and the odds against rain is 2 to 3. Did you follow how to do that? So to change a percent to a probability, first of all, we need to change it to a decimal and change it to a fraction and simplify it to lowest terms. Percent always means out of 100. So anytime you have a percent, take that number and put it over 100 and then reduce it all the way down. So there's your probability form. This is your probability P of R. Now, that means for rain is 3, and the others left over out of that 5, that's why against rain is 2. I may be really explaining something you got to start with, okay? But we've got a chance to look at this one more time. Got another example right here. So the odds of winning the Powerball jackpot are 1 in big old number, 292,201,337. Now, honest, I looked this up because I just thought it would be an interesting thing to look up. You know, Powerball, I don't know if you know anything about Powerball. In Alabama, we don't have the lottery right now, but most states do. In Powerball, you select 5 numbers, 1 through 69, and then you select a 6th number completely separate, that's 1 through 26. And then if you get all those right, then you earn a whole lot of money, at least $40 million. But anyway, okay, when I looked this up, it said the odds of winning the Powerball jackpot are 1 in a number. But that is not odds. That's probability. If you see 1 in 5, that means it's not 1 to 5, it's 1 in 5. That's a probability. Odds are really always something to something. So if I want to convert that to probability, because it says the odds, let's get a pen working here. It says the odds of winning Powerball are, and so this is odds. Okay, now it says what is the probability that you will win? So that means we have 1 chance, and how many chances are there? So 1 chance we'll win, and 292,201,337 that we'll lose. Now, what is the total? Well, we're supposed to add these two guys together to get the denominator. That's exactly what this statement that I circled above is. So 1 plus 292,201,337, which of course is 1 over 292,201,338 is the total. Okay? That makes sense? So whenever you're given odds, you have to add them together to get the denominator. I thought the next one was, it's amusing, okay? It's not cute. It's amusing, though. It says the odds of being killed by an asteroid impact, which is 1 to 74,817,413. It says, what is the probability of being killed by an asteroid? That would be 1 in, right? This is odd, so it's 1 to this. So how do we find the denominator? We add them together again. So 74,817,413. The reason I wanted to do this is because, look, your odds of getting hit by an asteroid are actually a good bit better than your odds of winning Powerball. That's so fun. But they are. But people actually win Powerball, and I don't know anybody that's been hit by an asteroid, but there you go. And it says that was according to The Economist, which is a publication. So what do they know, right? Okay, so I hope this conversation about probability helped you out. We talked about the law of large numbers, and we talked about converting from probability to odds, and then from odds back to probability. If you have any questions, of course, let me know, and I hope you have a wonderful day.